All right, we've taken data, we've made our graphs. Now let's go through the analysis questions and consider what these graphs mean and some basic features of them. So for our distance versus time graph that we have up here, the basic shape of the graph is it's a curve. It's not linear anymore, now it's curved. And it's not just any curve, it is a curve that curves upward. So my students often say an upward curve. Now if we connect the dots, which we've sort of done, but not really. We've done a best fit line. We haven't actually played connect the dots here. Does the steepness change? Now, let's consider that we can show that by adding, by focusing in on just those guys, and then let's apply to series data 2 a linear trend line. And we don't need an equation for this. I just want to look at that, and now applying to series data 3 and also a linear trend line. Let's just take a look at those guys. So if we look at the two dots on the left, we get a trend line that's that steep. If we look at the two dots on the right, we get a trend line that is now steeper. I would say that that's a rather significant. Yes, it does change significantly. It gets steeper. And remember, as we discussed in the previous lab activity with the car, the steepness of the line corresponds to how fast it is, how fast the object is going. So since the steepness of this line changes, it goes from being relatively shallow to being steeper, that tells us that the speed of the ball increased as it went down the ramp. You should have also seen this. As the ball started at the top of the ramp, it was not moving, and then it was moving very slowly. And then by the time it got to the bottom of the ramp, it's now moving much faster. So it tells us that the ball's speed increased as it moved down the ramp. Right, because the relationship between distance and time and speed is that the speed is the slope of the distance versus time graph. Because what we're going to be doing, when you find the slope, you're doing a change in y, which is measured in centimeters, divided by a change in x, which is measured in seconds. So you end up with a quantity of velocity, since we have centimeters per second. Now let's switch over and take a look at our final speed versus time graph. And we don't need to sketch it on the axes here because I have it open on the left side here. The equation, 28x plus number. The shape of the graph, this shape of the graph is linear, and it's not just linear, it's also diagonal linear. So diagonal linear. Now what does that tell us about the motion of the ball? Well, as we move to the right in the time axis, the velocity increases because we're also moving upwards on the velocity or the speed axis. So as the ball rolls for a longer time, it moves faster, or its speed increases. Its speed increases, which it should be telling us the same story as the other graph is telling us, because they're both describing the motion of the same object during the same time period. They're just doing it from two different aspects. One is a straight up distance measurement, and then the other one is looking at the speed of the object directly, or an attempt to. All right, the slope of this graph, if we take a look at this, remember slope is change in y divided by change in x. And so this time the change in y is going to be measured in centimeters per second, and then we're going to divide that by seconds, which gives us centimeters per second squared. That's units of acceleration. So the units of acceleration here that's going to be the slope, that's 28. It should be the same as the average acceleration over here, 28.1. That's not too bad. So I got 28 versus 28.1. So average from the table is 28.1 minus the slope, 28. And then we're going to divide by 28.1. And then to make it a percentage, we'll multiply by 100. And in this case, I'm getting a percent error of 0.4%. And I put the absolute value bars there because we don't really care about is this over or under, just how far away from the bullseye are you. And in this case, it's 0.4% off. In my class, with our lab equipment here, 0.4% is absolutely amazing. This is very rare to see this good data. Now let's go back to our distance versus time graph and say, okay, can we see that 28 somewhere here? Well, not directly, but it's in there. Well, how does the number 14 relate to the number 28? Well, it's half of it. So half of that acceleration shows up here as the coefficient in the distance versus time graph. Here, the acceleration is the slope of the velocity versus time graph. And if we come over to the acceleration versus time graph, that acceleration is the y-intercept. And if you take a look at this, if you move up the y-axis, the vertical axis on the acceleration graph, you're already measuring it in centimeters per second squared. We're already looking at an acceleration kind of thing there. So however far up you are on the vertical axis here, you're already looking at the acceleration directly on this graph. So it should not be surprising that it's 28.4. Also, since the steepness of the incline did not change all the way down, it was the same steepness from the top to the bottom, it should be a pretty steady acceleration. And that's what we get out of this graph. What we get is a very horizontal line out of this graph. It's not exactly horizontal because I was timing things by hand, but it's pretty close. I'm happy with this. This is a good one. Key features. When you have an object that is accelerating, that is speeding up, you're going to get a distance versus time graph that curves upward, a velocity versus time graph that is linear but diagonally upward, and an acceleration graph. My computer will let me click here. The acceleration graph is going to be horizontal with a non-zero y-intercept here. These features are going to be pretty consistent for all uniform acceleration situations. And the next thing that I'm going to want to do is take these graphs and these specific equations and generalize them to go to other situations that also have uniform acceleration as a key feature.